My name is Yoav Alon at the University of Bristol, and today I want to share our recent research with Cristina David, where we discuss if graph neural networks can be used to estimate program termination, and also if we can extend them to localize the reason for non-termination. Termination analysis describes a classical decision problem in computability theory, where program termination has to be determined. In 1936, Turing proved that a general algorithm that solves the termination problem for all possible program input pairs cannot exist. But it is critical for many applications, such as software testing, where non-terminating programs will lead to infinite executions. The majority of techniques to determine program termination employ formal symbolic reasoning that comes with a number of limitations. They have to be specific to a particular type of program. They generally require some form of symbolic reasoning, which can be expensive. Verification conditions may be expressed in undecidable logical fragments, or may require extra program invariants for the proof to succeed. Beyond formal approaches, various attempts have been made to achieve formal proofs using neural networks. For instance, Jacobi introduced an approach where neural networks are trained as ranking functions. A similar idea is employed in the approach of Abate, which uses a neural network to fit ranking supermartinials over execution traces. However, the majority of these approaches continue to rely on formal methods to provide a strong soundness guarantee and consequently suffer from similar limitations. We therefore move away from strong correctness guarantees and we attempt to estimate a program's termination behavior and to localize the likely cause for non-termination. Finally, we suggest a debugging workflow for non-termination bugs. In the presentation, we only will cover the first two items. In recent years, graph neural networks have become increasingly popular for their ability to analyze graph structured data and to solve problems in all areas of life, from chemistry over social networks to knowledge graphs. And an obvious choice seems to be considering programs as graphs for their graph-like structure. When we consider the use of recurrent neural networks, for example, a large part of the model's capacity is actually used to learn context and hierarchy, where it actually should be learning to solve a specific task. The conversion of a program to syntax-tree representation preserves the program's hierarchy, and the program can be reconstructed from the graph without loss of information. In this running example, this is of course a non-terminating program. We can easily figure out which input combinations will lead to infinite loops within this nested loop. At the right side, we have the syntax-tree representation. In order to generate a readable representation that can be processed by a graph neural network, we must identify unique nodes and convert them into feature vectors. We obtain a local feature graph with one-hot encodings for all unique syntax tree nodes. And then we perform the operations of message parsing, or so-called graph convolution. Basically based on two steps. First, the aggregation of neighbor features, and second, the update of a target node. The main difference of most approaches is in how the update is performed. For example, summing up the normalized neighbor embeddings, using multi-layer perceptrons in order to update. But specifically for programs, information value of neighbors might not be equally important for termination estimation. So instead of using weighted average, we use a function, the attention function, that calculates weights depending on embeddings of source and target nodes, allowing the node to attend to some neighbors more than others. We normalize the attention scores across the neighborhood and thus obtain the process of message parsing. When we then append multiple iterations of message parsing onto a sequential graph attention network, we also use, of course, activation functions in order to introduce nonlinearity. And then in the last graph attention layer, the node-wise learned embeddings are averaged in a way that they can be backpropagated and processed as one-dimensional vector to linear layers. Then the output of linear layers gives us a confidence score. So for a running example, there's a 90% confidence that the program is non-terminating. A good estimation. Additionally, we obtain the attention rates that can now be visualized into edgewise coloring. For a running example, we see that areas around the syntax nodes that cause non-termination are very high. But although there is some kind of intuition of node relation attention to the importance for classification, one must be very careful not to interpret them as non-termination reason. Sometimes a high attention score has no human understandable meaning. For that reason, the identification of non-termination patterns must happen in a second step. For non-termination, we want to identify the location of a non-termination reason. In semantic segmentations, which you might be familiar with from images, we obtain a classification and location. For graphs, that is basically a node-wise classification. We adapt the concept to programs and identify the location of non-termination reason based on an annotation of the outermost loop that caused non-termination. Now we can use node-wise cross-entropy loss and train the attention layers. Attention scores are different if tasks are different. For the same program, different attention scores might be obtained than for a classification task. Good data is of course key to training successful models. This also posed the main challenge to experiments. We got 4 datasets for classification and 2 for semantic segmentation, whereas 2 of our classification datasets are part of benchmarks, which of course are not enough for training and are not balanced. For that reason, we had to construct training sets of identical node distributions and use the benchmark datasets as validation. For semantic segmentation, the annotation of a loop that causes non-termination was necessary to generate sufficient data. Detailed metrics are in the paper, of course. We tested different layers, different experimental configurations. But some insights are that usually non-termination patterns are easier to identify. That we obtain better results if we use graph convolutions that use attention. And additionally, that when using graph attention layers, the self-attention can be used to obtain edgewise importance for termination. For semantic segmentation, we showed that we can identify the cause of non-termination with a very high accuracy. Metrics are generally high, but of course data is key in order to generalize well for different programs. To sum it all up, we estimated programs' termination behavior using graph neural networks. We were able to localize the cause of non-termination using semantic segmentation. And we also provide a prototype on GitHub. We are very happy if you try the prototype and also to receive your questions.